Let's apply Ampere's law to the case of what we call a coaxial cable. We'll start by considering the fact that any simple appliance could be modeled as some resistor, some load over here, and it requires a current being delivered to it and a current being returned from it to and from a power supply to form a complete circuit. So if this is your appliance, then your power cable for any device typically has to allow the current to go to the device and then back again. So it's like a bundle of two wires. Now, a single wire produces a magnetic field like this, as we've seen, if this current here is coming out of the page. But a power cable like this here has both your delivery and return wires side by side like that, packaged together and surrounded in insulation. So in cross section, this wire here looks like this, where you've got one wire delivering current out of the page, next to it a wire delivering current into the page, and they're bundled and surrounded by this insulation. Each of those currents is generating magnetic field in the surrounding environment, so we get fields kind of like this around a power cable of this kind. Now, there are certain cases in which we would like to be delivering power, but without polluting the surrounding environment with magnetic field. And that's where the coaxial cable geometry comes in. Here we've got an example of a coaxial cable where there is an inner conducting wire surrounded by a layer of insulation inside there, and then an outer conducting sheath. This conducting sheath here is separated from the inner conducting wire by a layer of insulation in between. So in cross section, this wire looks like this. Here in orange for copper is our inner conducting wire. Then a flexible insulating material separates it from the outer conducting sheath. And this power cable provides the delivery current in the inner wire, let's say, coming out of the page, and the return current comes back around that surrounding outer sheath. So the return current would be going into the page, but spread out around this sheath. So wire current coming out through the middle and current going back in all around the outer sheath there. Okay, so that way, instead of having your two wires side by side, we have them, the delivery and the return current, coaxial, sharing this axis with each other. All right, so let's use Ampere's law to look at the magnetic fields in and around a coaxial cable. We'll start with locations inside our wire. We'll ignore the thickness of this outer sheath and the thickness of this inner wire to say they're both very thin, and say the wire as a whole has a radius capital R. So at locations little r less than big R, let's draw an Amperian loop inside here, and note that since that current enclosed is coming out, I'm going to use right-hand rule to specify that I'll be integrating counterclockwise around that Amperian loop here, this loop of radius little r. State Ampere's law. We're going to integrate B dot ds around that path. And note from our symmetry here, in the cases we've considered before, that we must have a magnetic field pointing parallel to our DS's at all of the locations on that loop. This B and this DS pointing in the same direction. We must have a magnetic field line, B field line like that, lined up with our Amperian loop, as we've seen before. Our currents enclosed would be the current being delivered on this thin inner wire coming out of the board. So our evaluation here is what we've seen before. B and DS are in the same direction. B is the same value in magnitude at all points on that path, so it comes out of our integral, add up all the ds's, and we get the circumference of that circular path. And our current enclosed, the current penetrating through this open surface bounded by our Amperian loop, that would just be this inner current here. The outer return current is not passing through the region bounded by our loop. So current enclosed is just plus I on the inner wire coming out of the board. Okay, so we have here our magnetic field in that space between the inner wire and outer sheath, given by this now familiar formula. Okay, but what about outside? R greater than big R. If I want to find the magnetic field out here, I need an Amperian loop located out here. So let's draw a path utilizing our symmetry, a circular path with some radius little r, now greater than big R. And once again, we'll circulate counterclockwise around this loop and apply Ampere's law to this. Stated again, B dot ds equals mu naught times the I enclosed. And this time focus first on the right-hand side, the current enclosed inside this big Amperian loop. So all the current penetrating through this open surface bounded by our loop. Well, that'll include the current on the inner wire, that plus I coming out, and also the currents going into the page through the outer sheath here. Now, if the current being delivered is the same as the current returning, then the total current coming through the outer sheath is also I, but it's going into the page, which by right-hand rule is our negative current direction. So our current enclosed is the current on the inner wire plus the current returning through the outer sheath, which is a plus I, and then from the sheath, the current into the page is a minus I. The net current penetrating through our Amperian loop is 0. The total current enclosed is 0. And the only way that can be true is if on the right-hand side, since ds is non-zero, and by symmetry we know b can't be perpendicular to ds, the only way this can be true is if b is 0 also. Therefore, no magnetic field outside of our coaxial cable. Graphing those results. B as a function of distance from the center of the inner wire. There is big R, the radius of the sheath. So we have this function for R less than big R. So that function, and as soon as little r equals big R, and we go outside of the sheath, then the total current enclosed is 0. So this drops suddenly down to 0 right at the sheath. So we get this 1 over R function, and then a discontinuity going to B equals 0 outside. The great benefit of our coaxial cable here is that it does not produce any magnetic field on the outside. So our picture of it would be inner wire, insulating material, outer sheath, and we will have B field on the inside here, but B equals 0 out there, so that you can embed this cable in amongst other electronics and not be generating a magnetic field that will be interfering with surrounding electronics.